Today we will explain a very simple example of how to find the second shortest path in a directed weighted graph. This algorithm is very useful nowadays as it has very wide range of applications such as in computer networking, roads networking, and others. Here we have a few of vertices and edges, connect them. Start vertex I and destination vertex A. This algorithm is used to find k-shortest paths in a loopless graph with non-negative edge cost. It depends on Dijkstra algorithm. So we will apply Dijkstra algorithm in order to solve this problem. What is known about Dijkstra algorithm is that when we apply it on a source node in a graph, it will find the best path from each other node in the graph to the source node. Also, each node has its own best edge that leads to the source node via the best edges of other nodes, which gives us the best path from that node to the source node. For that reason, let us consider this inversed graph which all edges have the same weight but inverse direction. We will consider the destination node is the source node and we will apply Dijkstra on it till the algorithm visits all other nodes. For this time we don't need to determine the destination node. But let us consider the destination node is the same source node I, colored red. Source node A is colored green.
As we apply the algorithm, we will get the shortest path from A to I, which is colored here with green and with the cost 37. And as we mentioned before, we will run the algorithm until every node in the graph is visited. Because in some cases the algorithm may stop when it finds the shortest path to the destination node we choose. In addition of finding the best path from source node to the destination, the algorithm will find the best cost from each node to the source node, as it is shown in the table. In the column named shortest distance from A, as you noticed in the table, the algorithm gives us the previous node of each node, which determines the best edge we talked about. The best edge of each node in this graph is colored orange. And for the nodes those belong to the shortest path are colored green. If we need to know the best path from node A to node F, for example, we will follow the best edge of F, which is here, connects F with B, and then the best edge of B, which connects B with A. Let us return the graph to its original state. But we keep the information we got from applying the Dijkstra algorithm.
The second shortest path between two nodes in a graph should contains at least the source node and the destination. Now let us iterate on the nodes those belong to the best path. In each node we should iterate on reachable nodes except those who belong to the best path. Programmatically we should have two loops. In the outer loop we should iterate on I, G, D and A. In the inner loop and when we are in node I in the outer loop, we should iterate on F and H. And when we are in node G in the outer loop, we should iterate in the inner loop only on F. Now iterate in the inner loop on F and E. When we in D in the outer loop, A has no reachable node to iterate on. In each iteration we should compute the difference between the shortest distance from A to both vertexes we are iterating on, plus the length of the edge connecting them. So in the first iteration, which is I, we will iterate on F and compute the shortest distance from A to F minus the shortest distance from A to I, plus the length of the edge connecting I and F, which equals 35 minus 37 plus 17 equals 15. Then iterate on H and compute the shortest distance from A to H minus the shortest distance from A to I, plus the length of the edge connecting I and H, which equals 41 minus 37 plus 15 equals 19.
Now in the big loop let us iterate on G, which has only F to iterate in the inner loop, and we get 35 minus 25 plus 2 equals 12. Also in the big loop we will iterate on D, and in the small inner loop we will iterate on F to get 35 minus 22 plus 17 equals 30. And on E to get 31 minus 22 plus 50 equals 59. Now all we got is this set of numbers 15, 19, 30, 12, 59. The smallest number is 12, which indicates two vertexes F and G. So the second shortest path will be the shortest path from A to F plus the edge that connects F with G, plus the part from the shortest path that is from the source node I to the one of the nodes we got that belongs to the shortest path, which is here G. And the path length is 37 plus 12 equals 49.
The part from the shortest path that is from the source node I to the one of the nodes we got that belongs to the shortest path, which is G, is colored cyan. The edge that connects F with G colored red. The shortest path from A to F colored orange.
The second shortest path we got is colored yellow. This algorithm can find the k shortest path. For example, if we need the third best path, we should take the second smallest value in the set, which is 15, and which indicates the vertexes I and F. So the third shortest path will be the shortest path from A to F plus the edge that connects F with I, plus the part from the shortest path that is from the source node I to the one of the nodes we got that belongs to the shortest path, which is here I itself. So this part here is actually missing. And the third best path length will be 37 plus 15 equals 52.